Hello, everybody. I hope you are doing well. This is lesson number 10 in Math 100. Lesson number 10 starts a new chapter on probabilities. So this lesson in particular is about probabilities, risks, and taking chances. It has some very important applications in terms of things like false positives and false negatives. And so I want you to pay close attention again because this is very applicable. I will start with some fundamental ideas of probability and we'll continue into the lesson 11 because that's also a continuation of probability and how to count. All right, so let's get started. And my background is appropriately all about probability. What is that one city that is based on probability and thrives on probability and risks and expected values? Las Vegas. All right, so here we go from Las Vegas, lesson 10. Okay, so lesson 10 is about probabilities, chances, odds, and risks. All right, and so I'll be talking more specifically about probabilities. Main questions involve things like how do you calculate chances, right? And by the way, we live by chances every single day. And a typical example, I'm not sure what you're wearing today, but if it's a very hot day, you look at the weather and you say, well, I think I'm going to wear short sleeves. Why? Because there are risks involved when you wear long sleeves in a very hot day, right? I mean, you're going to start sweating and you're going to be miserable and so on. But on the other hand, if the risks are not so big and if you feel like, well, I can get by, I like long sleeves, it may be okay. How do you get to the campus? What kind of car do you drive? What kind of route do you use to get to your destination? All of these things have to do with risks and chances. And so the probability is really a part of our life. And this will be more obvious in the next lesson when we talk about the expected value, right? But we will also address in our lesson number 10, about the false positives. If you get tested positive for a rare disease, for instance, how likely are you to actually be with that disease? And that is a very important question. In fact, it's a question whose answer I hope everybody, or I wish everybody would learn, because that turns out to be a pretty important thing in terms of our health. Okay, I will start this discussion with this thing called the birthday problem. There's a famous problem involving probabilities called the birthday problem. Okay, you can look it up if you want. I'm sure that the internet has tons of information about the birthday problem. So here's how the problem is stated. What are the chances, what's the probability that at least two people in the same room share the same birthday? Let's say, you have this room, you only have two people, right? You and somebody else. What is the probability that those two people, you and another person, share the same birthday? And the answer is, assuming that we have 365 days in a year, let's just assume that nobody is born on February 29th. I know some people are, and they often choose either the March 1st or February 28th to be their, sort of unofficial birthday. But if every if every year has 365 days, the probability that you and the other person has the same birthday is 1 out of 365, which is about 0.274%, not even 1%, obviously, right? Okay, if three people are in the room, what happens to this probability? What is the probability that at least two of these people share the same birthday? Now, you can probably guess it's pretty rare that this will happen. Now, I am not saying, listen carefully, I am not saying, I'm not saying that the probability that one of these other two people have the same birthday as you, okay? Because in that case, we are specifically saying as a particular day. Okay, that's not the question. The birthday problem asks, what is the probability that at least two of these people were born on the same day? And it turns out to be still less than 1%. It's about 0.82%. Not surprising, right? What is surprising and what is interesting is by the time you have 25 people, now I'm not going to put a bunch of points here, but if you have 25 people in a room, okay, it turns out that the probability that at least two people share the same birthday is 57%. In fact, it's more likely that at least two people share the same birthday than not. Okay, and that is surprising because it only takes like 25 people, and then it becomes more likely that the two people share the same birthday than every one of the 25 people having different birthdays. This is hard to believe. Okay, and in fact, when you have like 50 people or something, it's almost certain that a few people share the same birthday. Okay, so how do you figure these things out? Okay, well, we have to start with some basic ideas on probabilities. Right. We will not pursue this very much anymore. If you want to do a project later on the birthday problem, it is a fascinating topic, and maybe some of you can do your course project on the birthday problem. Okay, let's go back to the beginning. Right? Probability theory starts with defining this an event. What is an event? Event is anything that could happen. Okay, event could be that today is sunny. An event could be that on the roll of a die, I get a 1. An event could be that I get to pass this course, whatever. If E represents an impossible event, okay, let's say that on the test that is worth 100 points, I get 300 points on one test. That's impossible. We say the probability of that event is 0, okay? If E is a certain thing, okay, so today is Monday. What is the probability tomorrow is Tuesday? That's certain. So such an event has 100% chance, and that is 1. Okay, sorry, you don't write 100. It's just 1, which is, of course, equal to 100%, okay, in terms of the percentage. For any other event, we define the probability to be between 0 and 1. Okay, so this is impossible, this is certain, everything else is between 0 and 1. So that's one thing you should remember, and it's pretty obvious that the probability of any event is between 0 and 1. Now, the word outcome is used in a very specific way. An outcome is a basic possible result. Okay, so this is like an element. This is like an atom. It's an unsplittable result. An event, we talked about events here already. An event is one or more outcomes, and I will explain exactly what I mean by this. Okay, now again, pay close attention to this word event and an outcome. These are two different things. I mean, they could be the same in some situations. All right, so for instance, let's say you flip a coin 3 times. Okay? Or equivalently, you can flip 3 coins at the same time. It doesn't really matter. But when you flip a coin 3 times, there are, it turns out, 8 outcomes. Okay? In fact, let's just understand this. Let's spell them out. You could get heads, 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 right? Certainly you can do that. You can also get heads, tails, heads, tails, heads, heads, tails, tails. And of course, I'm following a very particular order here, okay? I'm assuming that H comes before T. And so if you see that all these 4 outcomes have one thing in common, and that is that the heads is the first of the results of the flip, right? So I have 8 outcomes, all starting with heads. But of course, I can start with the tails, right? So it's tails, heads, heads, tails, heads, tails, 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 heads, and tails, tails, tails. Okay. This, by the way, is called a lexicographical or lexicographic order. And the reason, this is the dictionary order. And if you look at all the 8 outcomes, this is exactly in the alphabetical order, right? H comes first, T comes at the very end. So, and I listed all 8 outcomes. Now, you could also, and you may have seen this before, you could also illustrate this in what we call a tree diagram, okay? In the first flip, you can get a heads or tails, right? And if you get heads in the first flip, you can also get heads and tails independently on the second one. And regardless of the first 2 the results, you can get heads and tails. And so by the time you draw this tree diagram, you see that there are 8 branches, right? For instance, this first one here, this is heads, heads, heads. And so for each of these 8 outcomes, you see a branch. Okay, so this is called a tree diagram. And again, the number of branches has to be counted and has to be calculated in general. And this is something that we will be studying in lesson number 11. Okay, so what is the probability? Okay, assuming that you flip a coin 3 times, what's the probability that they all come out to be tails? Well, that's only one of the 8 outcomes, right? So we say the probability is 1/8, assuming that this is a fair coin and that the probability of getting the heads is 50% and probability of getting tails is also 50%. What is the probability of this one event that says ending with heads? Okay, so in other words, regardless of what the first 2 results are, the last flip results in the heads. So it's 1 here, 1 here, 1 here, and 1 here. Not surprisingly, it's 4 out of 8. And so that would be 1/2. The probability that the last flip ends in the or results in heads turns out to be 1/2 or 50%. Okay, let me give you an extra problem here. What is the probability of 4 heads if 4 coins are tossed? Okay, so if 4 coins are tossed, so you'll have like, another pair of branches growing from each of these branches. So you end up with twice as much as this. So you have 16 outcomes. Out of those 16 outcomes, the way to get 4 heads, the event of 4 heads, of course, is only one, right? You only have one of the outcomes corresponding to heads, 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 namely this very first one, okay, because everything else will be different. And so it turns out this probability is 1 out of 16. Okay, I hope this makes sense. Again, how do you calculate this number? Well, that's easy. This one is easy. It's 2 to the 4th. But typically, the counting turns out to be a very difficult problem, or could be a very difficult problem. And again, this is something we will be doing in our next lesson. All right, so here's a general formula for the probability of any event E. Okay, and that is assuming that these outcomes happen with equal probabilities. Then okay, so you do the number of ways E can happen. So if I pick the second example I did, which is this, okay, what is the probability that the last flip results in heads? And we actually counted 1, 2, 3, 4, and we said there are 4 out of the total number of outcomes. All right, so it's 4 out of 8, which is 1/2. So the general formula for a probability of some event E is a fraction, okay? And it's a pretty simple fraction, right? Okay, so that's what we call a theoretical probability or mathematical probability. Okay, now we have all sorts of probabilities, and one is called empirical probability because we can't assume that things happen with equal probabilities, like a fair coin or fair die or fair dice. Okay, so here's an example. Many things, so this is data-based. I think I've written this before, yeah. Actual data collected. And this is, what we use to study the chances of something happening. Like for instance, what is the probability that a certain candidate will win a presidential election, for instance? That would be a empirical probability. What is the probability that something is going to happen with the weather? Like for instance, what is the probability that a tornado is going to hit a certain area on September 1st, for instance, okay? And so that's based on the scientific data collected over many, many years, okay? So here's a simple example. Let's see that, and these are accurate numbers, by the way. You can look up these numbers. Free throw percentages by NBA players, actual figures. I prepared this back in 2019. Did not realize that one of them would no longer be with us so in such a short time. Michael Jordan, Kobe Bryant, and Shaquille O'Neal. Right? And so you are probably familiar with all these players. So what happened in their career? So these are the numbers of free throws they attempted in their NBA careers and the free throws made. All right. So the probability, the empirical probability that Michael Jordan would make a given free throw is this number divided by that number. Okay, so all you have to do is to, let's say this is A and B, and this is B divided by A, right? And so this is 0.83527. And so you can say this is the probability that a Michael Jordan would make a free throw was about 83.5%. Okay, for Kobe Bryant, this divided by this will give you 0.83688, also close to 83, slightly better, but 83.7%. And these are like the average of typical NBA, professional basketball player. Shaquille O'Neal was in a different league. I mean, it's the same NBA, but he did not have such success in free throw attempts. If you divide this number by that number, and you can do this on your calculator, it's 52.52746. And so this number is about 52. And this is an empirical probability question, which sort of shows you that Shaquille O'Neal did not have as good of a free throw percentage as most other basketball players. All right. On the backside, I'm going to mention a couple of things, right? And then we will go into another part of this video for lesson number 10. But a complementary event, this is easy, all right? Complement means the opposite, all right? And so it is the opposite of event E. So it's the event, or it's the event that E does not happen, okay? So what is the probability of the event that some event E does not happen? Okay, so if E is the probability that if E is the event that it is sunny tomorrow, then the negation of E, or the complementary event of E, is that it's not sunny tomorrow. Okay, so what is the probability that the negation of E happens, or not E happens? Well, that's pretty easy. The probability something happens, anything happens is 1. So all you have to do is to subtract the probability of E happening from 1. Okay, and that is the probability of not E. Find the probability that you do not get a 1 when you roll a die. Now, when you roll a die, okay, die is a singular word for dice, of course, and you have a 1/6 probability that you get a 1. So the probability you don't get a 1 is 1 minus 1/6, which is, this is 6/6 minus 1/6. You have to have the common denominator. This is 5/6. All right, and again, this is pretty simple, right? What is the probability? And this is where the complementary event becomes very useful. All right, what is the probability that you get at least 1 tails when you toss 3 coins? Now, you toss 3 coins before on the front. Okay, so you know exactly what those 8 outcomes are. And what is the probability that you get at least 1 tails? Okay, so E is to get at least 1 tails. Now, what you can do is if you list all 8 outcomes, you can get 1 tails. All right, so you have let me just use another color here. I have a tail here. Tail here, tails, 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 tails. So it turns out every one of them except the first one has at least 1 tail, right? 1 tails. And so the answer is at least 1 tails. This probability turns out to be 7/8, because 7 out of 8 outcomes has that. But a clever way to think about this, and of course, if you only have 8, you can list them. What happens if there are like 3,000 outcomes, or 13 million outcomes? Then you can't list them and count. I mean, you could, it's gonna take you a long time. So here you can find the probability of E as 1 minus the probability that not E happens, the complement of E. So what is the opposite of E? E says at least 1 tail. What's the negation of having at least 1 tails? Ooh, that sounds like what you learned in chapter 1. Opposite of at least 1 T. That is no T at all, right? So in other words, all heads. You see that? The opposite of having at least 1 tails is all of the flips result in heads. Okay, so this the negation will be all of it, every one of those three is heads. That's 1/8. We calculated this before, right? The probability that you get all heads in 3 tosses or 3 flips of a coin is 1/8. And so the result of the complementary probability is 7/8. Of course, that's the same as when we counted those outcomes. Okay. All right. Let me just give you this. Maybe you can fill this out and you can come back to this. Often probability questions deal with a set of cards, a deck of cards, a standard deck of cards. It has 4 suits, right? You have diamonds, spades, clubs, well, I missed some. Yeah, hearts, diamonds, spades, and clubs. And each suit has 13 cards. You have ace, which represents sort of like 1, and then numbers 2 to 10, and then jack for like 11, queen for 12, and the king for 13. Now I say this because most of you know this. Some of you may not actually have seen a deck or standard deck of cards. All right, so answer these questions. What's the probability that a randomly drawn card is a king? Okay, you can count the number of kings out of the this deck. And by the way, a standard deck has 4 suits and 13 types in each suit, and so that's 52 cards altogether, not including the jokers. And so what is the probability that a randomly drawn card is a spade or the queen of clubs or 7, 8, or 9 in any suit? Try to answer these questions, and then we'll come back to the second part of this video.